Okay, another example on conditional probability. And remember your formula, we derived it in a previous class. In this example, we're told there are 24 students in a class, 16 of whom are girls. Half of these 24 students study French. A student is selected at random from the group. F is the event that the student selected studies French. G is the event that the student selected is a girl. We're given that the probability of F given G is equal to 1.5 times the probability of F given G complement. And we're asked to complete a contingency table and a Venn diagram for the experiment. How many of the boys in the class study French? Okay. One thing I'm noting, I'm not actually being given probabilities here. I'm being given cardinal numbers, but we can work everything out in pretty much the same way. We're not given probabilities, but the probability of B given A can be written as the number of elements in A intersection B divided by the number of elements in A. Probability is just an extension of counting. So counting elements is what gives me my probabilities. So my conditional formula can be written in this way as well. So we're going to start off by thinking about a contingency table. There won't be enough information initially to fill the whole thing in, but we'll be able to get some information in there and then see where we're going from there. So the events are, first of all, event F, that the randomly selected student studies French, and obviously the row below that is going to be F complement, always the complement. That's F complement, the randomly selected student does not study French, and then we have a total. Okay, the rows have to complete all possible outcomes, so either you study French or you don't. Up here the student is a girl. The column next to that will be G complement, because either you're a girl or you're not a girl. And now I'm going to look at putting in some numbers in here. So it says there's 24 students in the class, so that's all together in the class there are 24 students. 16 of them are girls, so the sum of all the girls, well, that's 16, which straight away we can work out that means 8 students are not girls. It also says half of the 24 students study French, so half of 24 is 12. And we can work out there that has to be 12 as well, because they have to add up to 24. That's really initially all the information. There's information in here which we'll have to come back to in a second. But none of these, F given G, that is not a cell. F given G complement, that is not a cell within my contingency table. So maybe I might decide to do something like define a variable. I'm trying to find how many of the boys in the class study French. Okay? So, how many people in the class study French and are not girls? Let's call that cell X over there. We can work out that this would have to be 12 minus X, because together they have to give me 12. This would have to be 8 minus X, because together they have to give me 8. And this one would have to be, I think, X plus 4, because together they have to give me 16. 12 and 4 is 16. X and negative X cancel. X and negative X cancel. 4 and 8 is 12. That's my contingency table. That's what it looks like. We're trying to find out how many of the boys in the class study French. Ultimately, we're trying to find this. But first, we're being asked to complete a contingency table. So, how are we going to complete it? That is incomplete. We have variables in there, but we haven't everything we need. And I'm just going to rewrite this equation. So we're told that the probability that a student studies French, given that the student is a girl, is equal to 1.5 times the probability that the student studies French, given that they are not a girl. So we're going to use our probability formula. Now, we're not dealing with probabilities here, we're dealing with cardinal numbers. This isn't probability. This is 12 out of 24. I could change it to probability. That would be 0.5, 0.5. But, I'm just going to stick with the cardinal numbers. So the number of elements in F intersection G divided by the number of elements in G. That is how I find the probability of F given G. On the right hand side we have 1.5 times the probability of F given G complement. Well, that's the number of elements in F intersection G complement divided by the number of elements in G complement. So we have this equation, and I'm going to substitute everything I know in here, and I'm going to be doing it in terms of x. So the number of elements of F intersection G, well, that's 12 minus x, divided by the number of elements in G, well, that's 16. That's equal to 1.5 times the number of elements in F intersection G complement, well, that's what we're calling x, divided by the number of elements in G complement, well, that's 8. Okay, so what we have here is a little equation, and I'm going to solve this equation for x. 12 minus x over 16, well, that's equal to 1.5x over 8. Various ways to do this. What I might do is just multiply on the right hand side by the number 1, but the version of 1 I'm using is 2 over 2. Okay, I could use that. Or actually, another way, maybe I'll go with this way, is to use what we call the cross products property. And the cross products property says two single fractions are equal if and only if their cross products are equal. To take the cross product, I'm going to take 8 and multiply it by 12 minus x, and that's equal to 16 times 1.5x. So that's the cross products property. It says that two single fractions are equal if and only if their cross products are equal. AD is equal to BC. Where B and D are non-zero because division by 0 is undefined. So just solving this equation now, it's really straightforward from here. Expanding the bracket, that's 96, subtract 8x, is equal to 16 times 1.5. Well, 16 ones are 16, 16 halves are 8. Combine them, that's going to give me 24x. Okay, adding 8x on both sides will give me, not 66, sorry, 96 is equal to 8x plus 24x, that'll be 32x. And then finally dividing on both sides by 32, that will give me x equals 3. So that's all that equation solved over there. So now we can put that into the contingency table, into a Venn diagram, and answer the question. Actually, I already know the answer to the question is 3, but we'll come back to the question in a moment. Finished, completed contingency table. What does it look like? Well, we've got the events F and F complement. We've got the events B and B complement. We have 12, 12, 24. We have 8, 16. X is 3, which is this cell. F intersection, sorry, it's not B and B complement, it's G and G complement. G and G complement. I'm used to writing A and B. So F and G in this case. So F intersection G complement, that's X. We said that was 3. That has to be 9. That has to be 7. That has to be 5. Okay? Because 9 and 7, 16. 3 and 5, 8. 9 and 3, 12. 7 and 5, 12. That's my contingency table. I was also asked to draw a Venn diagram. Universal set. Big loop for F. Big loop for G. What's their intersection? Well, their intersection is 9. The complement of the union is 5. In F but not in G. In F but not in G is 3. in G, but not in F, is 7. Okay? And all those things should add up to 24. Because there's 24 people in the class. 5 and 3 is 8. 8 and 9, 17. 17 and 7, 24. What we were asked, how many of the boys in the class study French? So we're assuming that a boy is a non-girl here. So the number of boys studying French will be the number of non-girls studying French, which is 3. So 3 boys study French. Okay. Contingency tables, Venn diagrams, really useful tools for this kind of thing. You know, you can solve the problems without them, but personally I think they're very useful and I use them often.